Welcome students. In previous lecture we see the flux of field. Now today we are going to discuss about the expression for motional electromotive force. In Faraday's experiment we see that then there is a relative motion between magnet and coil, or conductor is moved in a magnetic field, then EMF is induced in that coil. So according to the principle of electromagnetic induction, when conductor is in a motion, either translational or rotational, in a magnetic field, then EMF is induced in it, and we have to derive the expression for that induced EMF in this process. So the first article from this is the translational motion of conductor and the expression for its motional EMF. So let us consider a figure. So what is in this figure? Suppose in this figure A, B, C, D is a rectangular conductor. So it has a 4 sides. The 3 sides A, B, A, D and D, C are fixed in a magnetic field. So here magnetic field is shown by these dots. So this is indicated by this way. That is, this plus sign indicates that this field is perpendicular to the plane of screen and directed inward. If this is indicated by that dot surrounded by a circle, then this field is perpendicular to the plane of screen and directed outward. But in this figure we see that this field is perpendicular to the plane of figure and directed inwards, and all these signs are equidistant, that is, this field is uniform. So field is not changing with the space or time. But the branch BC of this conductor is continuously moving towards the right with uniform velocity phi bar. Is moving with a uniform velocity phi bar. So if the branch BC is moved towards the right, its area goes on increasing. So though field is constant, area goes on increasing, that is, area changes, then EMF is induced in that conductor. So we have to derive the expression for this induced EMF due to the motion of conductor in a magnetic field. Suppose the length of conductor BC or AD is L, and which is continuously moving towards the right in a magnetic field. So suppose the straight conductor moving in uniform and time dependent magnetic field as shown in a figure, then induced EMF is given by equation by Faraday's law. The magnitude of this induced EMF, is given by equation that is equal to d phi by dt, where phi that is equal to, by definition, b into a cos theta. So theta is the angle between b bar and a bar, but here field is perpendicular to the plane of figure and directed inwards, and the surface vector is also perpendicular to the screen, that is theta is equal to 0, cos 0 is equal to 1, so phi that is equal to ba cos theta, and cos theta is equal to 1, then phi that is equal to ba. And what is a? That is the area of that rectangle ABC. If the AD is a length L and DC is a length x, if this length is x, suppose this length is x and this length is L, then its area is given by equation Lx. So we have E that is equal to BLx. So substitute the value of phi as a BLx in this equation. We have E is equal to dBLx by dt. So B, that is the induction of magnetic field, which is a constant. So here B is a constant. Now L, that is the length of conductor. If the conductor is moving towards the right, then there will be no change in L, so L also constant. So here B and L are constant, so take that terms outside the derivative sign. We have E that is equal to BL dx by dt. So by definition, what is the dx by dt? That is the rate of change of displacement, that is equal to velocity phi, which is given in this figure. Now substitute dx by dt is equal to phi. We have E that is equal to BL phi, and this is the expression for motional EMF due to the translational motion of conductor in an uniform magnetic field. What is that expression? E that is equal to BL phi. What is B? B is the induction of magnetic field. What is the L? That is the length of that conductor. And what is the V? The magnitude of its velocity with which it moves in a magnetic field. So this is we can obtain this expression on the basis of Faraday's law. So the same expression can be obtained by another way. So let us discuss about that other or alternative method. The same figure, the ABCD is a rectangular loop. The side AB is continuously moving towards the right. This magnetic field is perpendicular to the plane of figure or plane of screen and directed inwards. Suppose the length BC is L and moving with velocity V towards the right. So BC is a conductor, and we know that in conductor there are free electrons. In conductor there are a free electron. Suppose this is a conductor BC, and if there are free electrons and they have a random motion, but this conductor is continuously moving with a velocity phi in an magnetic field which is perpendicular to the plane of figure, then the force, magnetic force, will be acting on that all electrons which are negatively charged. It is found that these all electrons are experienced by a force, and that magnitude of force is given by QVB sin theta. So the force acting on that free electron is given by equation QVB sin theta, where Q charge on that electrons, that is N into E, then there is V, the velocity with which the conductor flows towards the right, B, that is the magnitude of induction of magnetic field, and theta is the angle between phi bar and B bar. Now what happens? Due to this force, the direction of this force is given by Fleming's left hand rule, and all of these electrons are pushed towards the below. So all electrons are connected towards the end B, then end B acts as a negative terminal. So all electrons are collected here, and the remaining end acts as a positive terminal. So all electrons are collected or gathered together at a point B. So this is reached in a negative potential, and this is reached in a positive potential, and which is equivalent to a battery. In this way, this conductor acts as a source of EMF, and we have to derive the expression for that magnitude of that EMF. So the force acting on that free electron is given by equation QVB sin theta. Now these electrons are experienced by a force. So there will be displacement of that electrons. The maximum displacement of electron is the distance between extreme ends of conductor, that is B and C. And we see that the distance B and C, so this distance B and C is the length of that conductor, that is L. So due to this force F, there is a displacement L of a electron. Then work done in this process on that charge is given by basic definition of work done, that is force into displacement, that is W, that is equal to F into L, and that will be equal to QVB sin theta into L. So this is the work done on that free electrons due to the magnetic force. But by definition, the work done per unit charge is an EMF. So we have to derive the expression for EMF. So we have E that is equal to W upon Q. We have E that is equal to W upon Q. Substitute the expression of W, we get phi B sin theta into L. So here theta, that is the angle between phi bar and b bar, that is a 90 degree. That is the angle between them is a 90 degree, and therefore sin theta is equal to 1. And when sin theta is a 1 or plus 1, then induced EMF is maximum. So E is a maximum when sin theta is equal to plus 1. Now substitute this condition in this equation. So when sin theta is equal to 1, we get E that is equal to phi B1 into L, that is E that is equal to BL phi. So this is the expression for motional EMF or EMF induced in the conductor when there is a linear motion of or translation motion of conductor in a magnetic field having length L moving with velocity v in a magnetic field of induction B. So B is the induction of magnetic field, L that is the length of conductor, and v is the velocity of that conductor. So on this problem there may be on this formula there may be problems of 2 marks. You are given B, L and V, and you have to derive the magnitude of E. There are a lot of problems in your textbook, it may be for MCQ. So this is the expression for the induced EMF when there is a linear motion of conductor in a magnetic field. But it is never always be a linear motion of conductor. Sometimes the conductor will be rotate in a magnetic field. So it is also a motion. So if there is a rotational motion, EMF is induced in the coil or conductor, and we have to derive the expression for the induced EMF when there is a rotational motion of conductor. So the next article, that is the induced EMF due to the rotational motion of conductor. So consider a figure. Suppose this is a conductor of length L. This is the conductor of length L as shown in figure. Suppose one end, this end is pivoted. So this conductor is fixed here and it is rotated along this pivotation with a uniform velocity omega. With uniform velocity omega. So the conductor of length L. So this is its length L. This conductor of length L pivoted at a one end rotates with a uniform angular velocity omega. So then there will be change in magnetic flux due to the motion of conductor, and we have to derive the expression for the induced EMF due to the motion rotational motion of a conductor. Now divide this conductor into smaller segments. So let us consider a small element dr at a distance r from the point of pivotation. So this conductor is divided into infinitely small elements, and consider one element of length dr situated at a distance r, and it is a continuously rotating in that magnetic field. So though conductor is rotating, that element is in a linear motion with a velocity v. So there is a linear motion of that infinitely small element dr, and we know the induced EMF. Induced EMF in that element may be dE, or consider dE, that is equal to B phi. We know that BL phi, B that is the induction of magnetic field, phi that is the linear velocity of that element, and dr that is the length of that element. So by previous expression we have dE that is equal to B phi into dr. Now the total EMF induced that entire conductor is given by integration dE. Therefore we have E that is equal to integration dE that is equal to integration BV into dr. But phi is a linear velocity, and linear velocity is related with the angular velocity, that is phi that is equal to omega r. Now replace phi by a omega r, then we have E that is equal to integration B omega r into dr. So B that is the induction of magnetic field which is uniform, and so that it is constant though there is a linear rotational motion of a conductor. Omega, that is a angular velocity. The conductor rotates with a uniform angular velocity. So B and omega both are constant. But there will be R changes along this integration. So take the constant term outside the integration, we get E that is equal to B omega integration R into dr. So we know the integration of R with respect to dr, that is R square by 2, and therefore if we solve that integration we get E that is equal to B omega R square by 2 having lower limit 0. So if this element is situated at the point of pivot, R that is equal to 0, and if the R is situated at extreme position, then upper limit, that is L. Then solve this equation, we get E that is equal to half B omega L square. So this is the expression for induced EMF in a conductor when it rotates in a magnetic field of induction B with uniform velocity omega having length L is equal to half B omega L square. So this is the expression for induced EMF when there is a rotational motion of conductor. So in this lecture we derive the two expressions for the motional EMF when there is a linear motion. So when there is a linear motion, E that is equal to BLV, and when there is a rotational motion we have E that is equal to half B omega L square. We can compare these two equations, and two equations there are lot of problems. You are given B omega and L, and you have to derive the E when there is a rotational motion of conductor. So this is about the motional EMF, so conductor moving in a uniform magnetic field.